afternoon to one and all. I am R.V. Kiran, Assistant Professor, Department of Mechanical Engineering. Today in this video lecture, I am going to explain you second model in this Coriolis component of acceleration, and this is the second problem in this type, that is in the Coriolis component. In the previous class, we have shown the what is a Coriolis component of acceleration, and we have defined a problem on it. And this is my 27th lecture regarding to the subject kinematics of machinery. So this is the second model problem in the Coriolis component. So first of all, study the question briefly. So the figure shows a quick return mechanism, and link 2 rotates uniformly at 20 radians per second in the clockwise direction. Determine the angular acceleration of the link 3. So that is the given problem statement here. So the given figure shows the quick return motion mechanism. So we can show it in the figure also, which has taken to a scale 1:5. So 1:5 scale we have taken. So what is meant by the scaling 1:5? So if we have a original length of 100 mm, we are going to take it as 20 mm, that is the 1:5 ratio. So this is the original one and this is the scaled unit. So this is the 100 mm. For example, it is 100 mm, and this is fifth part of the original scale, that is 20 mm. So that is the scaling of 1:5. So we can take any type of scaling, that is 1:5, 1:10, 1:20. So we can take any scale according to the our preference and usage. And in this question, it shows a quick return mechanism, and this link 2 rotates uniformly at 20 radians per second. So this is the link 2 which rotates clockwise in direction. So it has an angular velocity omega 2 and it rotates in the clockwise direction, and it has a angular velocity of 20 radians per second. So 20 radians per r by s means radians per second in clockwise directions. So in this mechanism, this is the first link which is fixed, and second is the link 2, and it is the link 3. Determine the angular acceleration of the link 3. So we have to find the angular acceleration of the link 3. And we have the given length, that is the length of 3 links. That first one is the OC, that is 350 mm. So this is the OC line, which is the fixed link. So first link is the fixed link, that is the 350 mm, and OA is, so this is the A link, So that is the OA is 150 mm. That is on the link 2. So the A position is on the link 2, and CB is equal to 250 mm, which is on the link 3. So this slider has different points. సో మనకి స్లైడర్ లో డిఫరెంట్ పాయింట్స్ ఉంటాయి మన స్లైడ్ అయినప్పుడు. సో అందుకని మనకి ఏ అనే పాయింట్ బి అనే పాయింట్ రెండు కూడా మనకి దీని మీదే వస్తాయి. సో ఏ అనే పాయింట్ వచ్చేసరికి లింక్ 2 లో ఒకటే వస్తుంది, బి అనే పాయింట్ వచ్చేసరికి లింక్ 3 లో ఒకటే వస్తుంది. సో we got the 2 points in it, A and B. So A is in the second link and B is in the third link, that is in the link 3. And next we have given the angular velocity of the second link, that is 20 radians per second. That is the angular velocity. Of the link 2. So we have given the angular velocity for the link 2 only. So we are taking the angular velocity as omega 2 is equal to 20 radians per second. So next, velocity of A can be taken as, so the A point is in the link 2 only. So link 2 మీద A point ఉంటుంది కాబట్టి, so we can take the velocity of A as omega 2 into OA. So the length of the OA link into angular velocity of the second link. So we have known the OA length as 150 mm and omega angular velocity of the second link as 20 radians per second. So in total we get the value 3 meters per second. So this is the velocity of A, that is we got 3 meters per second. So we got the value as 3 meters per second. So this is the space diagram drawn from the velocity diagram. Sorry, from the mechanism. So we have drawn the space diagram from the given mechanism. So from the given mechanism we have drawn the space diagram. So these are the given links here, OC, OA and CB. So first we learn to draw the OC link. So OC is the fixed link, that is the first link is the fixed link. So we have drawn the dotted lines here. So from O we are going to draw the line A. So that is OA length is 150 mm. So take the 150 length in the compass and take OA as center, draw an arc. So from the center O with a length of 150 mm, draw an arc. Next, from the line point C as center, take length as 250 mm. So the second length is 250 mm, and by taking it in the compass, the total length of 250 mm, draw another arc intersecting at the first line. That is the first intersection line. So we got the points A and B. So the same point is connected to 2 points, that is A and B. So we have drawn the space diagram. So here I have taken the scaling as 1 centimeter is equal to 5 centimeters. So 1 centimeter is equal to 5 centimeters I have taken. That is, I am reducing the scaling ratio. So I have taken the same scaling for the space diagram. So I have taken the 1 centimeter is equal to 5 centimeters. So here the length of the OC is 350 mm. So here I am taking the total 35 centimeters, but I am taking the 7 centimeters only. So the length of the OC is 7 centimeters and the length of the OA is 3 centimeters and the length of CV is 5 centimeters. So that is the scaling I have taken for the 1 centimeter, 5 centimeter scaling. So like that we are going to draw the space diagram. So I have drawn the space diagram according to the scale. 1 centimeter is equal to 5 centimeter scaling. And next we go to the draw the velocity diagram and the acceleration diagram for the Coriolis component of the given mechanism. So next we are going to draw the velocity diagram with the help of space diagram. So first we need to find the velocity of B, that is AB. So in the first equation, velocity equation is, that is velocity of A. So we are taking the velocity of A as velocity V plus AB. So velocity of B plus velocity of AB. So in the first point, draw OA as 3 meters per second. That is the given velocity. That is OA. The OA length is 3 meters per second, which is perpendicular to the link 2. So we are going to draw the perpendicular position of the link 2. So this is the link 2. So therefore we are going to draw the length. So this is the OA, which is perpendicular to the link 2. Next, from A, draw a line parallel to both of the slider. So this is the slider. We are going to take the same line, that is the parallel line from the point A. So from point A, draw the slider AB, which is parallel to AB. Then draw a perpendicular line to the link 3. So this is the link 3 and we are going to draw the perpendicular line, that is like this. So this is the perpendicular line. So the same line is drawn to the OB line. So OB is parallel to this line which I have drawn. So drawing that. So we have observed the points OA and B because OC points are fixed points. That is why I am taking the 2 points in same point, that is the same intersection of point. So then we are going to find the velocity of AB and velocity of B. So we are going to find these two lines. So first of all, velocity of AB is taken as AB into scaling, that is the measurement of the scale. So AB length, so that is AB length is 260 mm, that is 2.6 meters into 1, that is 2.6 meters per second. So we have taken the scaling as 1 and the length of the AB line, that is 2.6. So the obtained length is 2.6 meters per second. So that is the obtained length, that is 2.6 meters per second. And next we are going to find the velocity of B, that is CB into scale. So Here velocity of B is this line. So this is the line for velocity of B. So from O to B we are calculating this line. So the vector OB is taken as velocity of VB. So we are taking the CB into scale. So we didn't get the value as OB length. So we are taking the CB length as 250 mm. So we are drawing that one. So 1.55 into 1, that is the measured length, into scaling, that is the 1. In total we get the value 1.55 meters per second. 1.55 meters per second. So that is the obtained value in the velocity diagram. So this is the velocity diagram which we have drawn through the 3 points. So that is the 3 points. So look it for a while. So we got the values for velocity of AB and velocity of B, velocity of AB and velocity of B. So in this we got to draw the acceleration diagram also. So the velocity diagram has been obtained, and from this we are going to draw the acceleration diagram also. So we got the acceleration equation, that is acceleration of A is equal to acceleration of B plus acceleration of AB plus 2 into omega of third link and velocity of AB. So this is the acceleration equation for the acceleration diagram of A. So next we are going to find the acceleration diagrams for the all the sections. So first one is the acceleration of the line, tangential acceleration for a link, that is 0. So that is A is a link which is attached to the fixed link. So that is link 2 rotates with uniform velocity. So therefore we are going to see it with the uniform velocity. So therefore we use to find the tangential acceleration of the magnitude which is unknown. But to the link 3, we are going to the parallel to the link 3. So there these are the obtained values for the acceleration of A and acceleration of AB. So that is 32.34 meters per second. So therefore we are going to draw the first one. So this is the acceleration diagram. So we are taking the 2 points in the same direction, that is O dash C dash. So when you are drawing to the acceleration diagram, we need to draw these O point and C point in the same line, and we use it to take the points as O dash C dash. So here I am taking the scaling as 1 centimeter is equal to 10 meters per second square. So I am taking it as 1 meter is, and that is 1 centimeter is equal to 10 meters per second square. So from the point O dash or C dash, draw the CX line. So this is the CX line which is drawn the dotted lines, which is parallel to the link 3. So this is the link 3 which is parallel. We are going to draw the same line, and from the X dash line, draw a line perpendicular to the C dash X dash. So draw a line perpendicular to this line, which is this is the line, tangential acceleration of B, indicating the direction of tangential acceleration of B. Then from the line A dash, so from the line A dash, draw the Coriolis component as, that is 32.34 meters per second, and this line is perpendicular to the link 3. So this is the link 3 and this is perpendicular to the link 3. That is A dash Y dash line, which is perpendicular to the link 3. So this is the acceleration diagram we have drawn. We need to find the necessity readings. So this is the acceleration diagram to be drawn. I have drawn this acceleration diagram. So we are going to draw the we are going to scale the original components, that is the tangential acceleration of V and angular acceleration of the third link. So we are going to find out these three links. So from the y dash line, draw a line parallel to link 3. So this is the space diagram, and from this we are going to draw the line from the y dash which is parallel to the link 3, that is CA or CB line. So I have drawn this, indicating the direction tangential acceleration of AB. So which is indicating the direction of tangential direction acceleration of AB. That is the tangential acceleration of AB. And next we need to find the tangential acceleration of B and angular acceleration of the link 3. So we need to find these two. So for the tangential acceleration of B, we need to draw the scale x dash b dash. So this is the x dash b dash length. So we need to scale these two lengths. So x dash b dash into scaling. So x dash b dash has been measured as 8.2 meters per second, and the scaling is 10. That is, here we are taking the 1 centimeter is equal to 10 meters per second square. So I am taking it as 8.2 to 10. That is total 82 meters per second square. So we have taken as 82 meters per second square. Then we need to find the angular acceleration of the link 3. So for the angular acceleration, we need to find the tangential acceleration of B and the length of CB. So here we got the tangential acceleration of B as angular acceleration of the third link into CB, that is the length of CB. So by getting the angular acceleration of the third link to the left side, we got the values as tangential acceleration of B divided by CB. So in total, we got the values as tangential acceleration of B is taken as 82 meters per second square, and angular acceleration is taken as tangential acceleration of B divided by CB length, that is the CB length. So 82 by 0.25. So the length of CB is 250 mm. So I'm taking it as 0.25 meters. Therefore, it is taken as 328 radians per second square. So the angular acceleration for the given Coriolis component is 328 radians per second square. So that is the find out value for angular acceleration of link 3. So this is the procedure. So for the given diagram, you need to define the inputs first and then draw the space diagram. So this is the space diagram to be drawn. So after drawing the space diagram, you need to draw the velocity diagram from the find values from the velocity equations, and then you need to find the acceleration diagrams. So this is the procedure for the given problem. Thank you.